All right, so number 13, again, deals with parallel axis theorem, just like number 8 that we just did. So hopefully you are cool with that one. So 13, what are we on, 11.3? Why does this keep doing this? I don't know. Okay, so here we go. So it gives you this weird shape. Oh, fail. All right, and then it gives you the dimensions. This side is A, this side is B, the height is C. And we want to find out what the rotational inertia of this thing is, and it gives you the dimensions. So this is 3.5 centimeters, B is 8.4 centimeters, C is 1.4 centimeters, and then the total mass is 0.172 kilograms. Okay, so I'm trying to think if there's a shortcut you could take that doesn't involve using the parallel axis theorem. So let me show you what I had in mind when I assigned this, because you have to know the parallel axis theorem. And then McKeever, I'm interested in knowing what you did and how it's different. Okay? But let me do parallel axis theorem. So the idea is, again, if you go back to this sheet, somewhere on there is this guy. I is 1/12 m times a squared plus b squared. Okay? So that represents the rotational inertia about the center of mass, right? Follow? So I can find I about the center of mass. It's 1/12 of the mass times a squared plus b squared. So 3.5. I'm going to use kilograms centimeters squared because I'm being lazy. Is that cool? Is that going to mess anybody up if I just leave it in centimeters? Yeah, we've done it. It's fine. All right. So just know that if you were to find like rotational inertia or torque or something, you would have to switch to meters. Okay. All right, so anyway, so this gives you a number. Anybody know what it is offhand? No? Okay, whatever. It gives us a number, right? Okay. What is it? 1.8? Cool. So, and that's what? Kilogram centimeters squared. All right, so then the other thing we need to do is figure out what mh squared is. So, h is the distance from my center of mass, right? So you just do Pythagorean theorem. That gives you your h. So let's see. So h squared ought to be, well, half of a squared plus half of b squared, right? Right, because you've got this little triangle here. So 1.75 squared plus 4.2 squared, right? And that is h squared, right? Yes? C does not matter, correct. And same thing here, right? Like on this shape, the thickness of it doesn't matter. What's important is that it's of uniform thickness. Cool? All right, so once you get your h, you can find mh squared and then just add these two values, right? Cool if I stop there? Okay. McKeever, what'd you do that's different? Is there an easier way to do this that I'm missing?
Yeah, I just treated it like, I don't really have the sheet of the rotational inertia in front of me, but I treated like one big, like this one, the one big one, rotating about the center, and then I divide by 4. One big one.
Why did you, dividing it by 4 would make it smaller.
No, because that's like one. That's like one.
Oh, that is really slick. I see. So what you did, all right, this is slick. All right, so here's what McKeever did. This is super cool. Totally blew my mind there. So what he did is he said, all right, we've got this shape. that looks like this, right? He's saying that that's a quarter of a thing that looks like this. Where the dimensions are just twice as big. And he said that any quarter of this is the same. So he found the inertia of this imaginary thing and then divided it by 4, right? Because each chunk, 1, 2, 3, 4, should have the same rotational inertia. That's super badass. That's really cool. All right, and I like that because that gets back to this idea that we can calculate the rotational inertia by adding chunks. So he sort of subtracted chunks in a sense, right? Very cool. Very cool. All right. Questions on that, you guys? Very neat. Very neat. All right.